All right, live at the palace again. All right. So we're looking at arc length, area of a sector. There's the formulas. Jackie, just pause it, copy it down because we're moving on. All right. So now we got angular. We're going to be learning today. So we got our arc length and area of a sector, but we're going to be extending that today and be looking at angular and linear velocity. Now, angular velocity, I'm going to introduce a new variable today called omega. And just say that because it was a commercial when I was in high school, a sports commercial. There was a sports store called Omega Sports. And they would always go, omega. All right, so anyways, angular velocity, which is omega, and it's equal to theta divided by t. All right? Now, what is angular velocity? Angular velocity is going to be taking the angular displacement, which is how far the angle, how many spins you get or how far the angle travels, and I'll talk about that, how far the arc travels and how long it travels per unit of time. Think of it this way. Remember in middle school when you did distance equals rate times time? You remember that?
Yeah.
And then if you wanted to calculate the rate of something, what did you do?
R. You would T over T.
No, you would do d over t. You do distance divided by time. Now I want you to think of this because angular velocity is trying to figure out how fast that wheel is spinning. So what it is, if you listen to the clicks, what happens every time you have a click? Let's spin a little faster. What's a click?
One revolution.
One rotation, which is how many degrees? 360 degrees. So every time you hear a click, how far did it travel? 360 degrees or
2 pi.
2 pi radians. So there's 3 ways you can measure that angle. This wheel's not very good. I'm going to use this one, even though this wheel didn't even measure right. Ooh, that one's awful. Use your new weights this one. Okay, this is just going to have to
Get
do.
your new one.
So anyways, every time you hear a click, it goes one rotation. So angular velocity is how fast that wheel is spinning. So for example, if I was to measure for 5 seconds, I'll start my watch. Okay? This is not going to be very accurate, but just go with it. I'm going to spin it. I want you to start counting the clicks as soon as I start my watch. Hold on. All right, ready? 1, 2, 3, start counting. Stop. About 12 clicks. So it has an angular displacement of 12 clicks in 5 seconds. So what happened is your distance traveled was 12 clicks. What does 12 clicks represent? 12 rotations, or 12 times 360, or 12 times 2 pi. Because one rotation is the same thing as 2 pi radians, which is the same thing as 360 degrees. Okay? Make sense? Still with me? So one rotation is 2 pi radians, which is also 360 degrees. So if it went 12 rotations in 5 seconds, you could say its angular velocity is 12 rotations per 5 seconds. 12 per 5. Okay? 12 revolutions per 5 seconds. Another easy example would be, okay, if I did 2 clicks, what would the angular displacement be for 2 clicks around the circle? 4 pi or 720 degrees or 2 rotations. Okay, that's 3 different ways you can measure angles. But here's the deal. What do we always want the angle measurement? So if it's in rotations, you got to convert it to what? Radians. It's 1 rotation per how many radians? 2 pi. If you've got it in degrees, you got to convert it to what? Radians. Anybody remember how we convert to radians?
Yeah.
You can do 2 pi as 360, or you can do as pi as 180. Either way.
They're not going to be all whole, are they?
Huh?
They're all not going to be whole.
No.
That's what I thought.
So that's angular velocity, and I think of it like this. It's really how fast that thing's spinning. Okay? It's how fast that wheel is spinning. I had a record player when I was a kid. You've probably seen CD players where they have this. Gosh, you're just a spaz. Come on, bro. Poor guy.
You need to
This
grease
won't
it
spin
up.
good.
Yeah, get your new one.
Get my new one. So here's the new wheel.
Oh, it's a
It's
beauty.
nice and smooth, but we can't hear any clicks is the only thing. But you can imagine the spinning, right? Like this wheel is spinning really fast. A lot of rotations per second, right? Okay? If you had a record player when you were a kid, you could change the speeds. You could go to like 15 speed, and the song would sound like this. Don't stop believing. Right? And then you play it at normal speed, which is like 45. Don't stop believing. All right, and then you'd play it really fast, and it sounded like Alvin and the Chipmunks. Don't stop believing. Okay, and it just speed it up, right? And on a CD player, it's the same thing. The actual CD, if you ever see it, it says 52x. You ever seen a CD player that said 52x on it or 60x? That's actually how many revolutions per second. The CD spins about 60 times per second. You ever pulled a CD player, pulled the CD out before it stopped spinning? Or like one that sits and you see the CD just spinning so fast and you like touch it and it even almost feels like your hands get a little friction and heat on it. Okay, that's sucker spinning. The faster it spins, the better. Did you know hard drives work that way? The faster the hard drive turns, the better. What does that mean? It's interpreting the data quicker. You want hard drives that have insane speeds. The faster the spinning, okay, the more interpreting the data. That data is going to interpret a lot quicker. Okay, so that's angular velocity. Well, what's linear velocity? Linear velocity is a little different. Linear velocity is v equals omega times r. Well, that's, okay, what I'm saying is I'm taking angular velocity. Don't worry, I'm going to explain a little bit more of this. Angular velocity. So I'm taking how fast the wheel's spinning, and I'm multiplying it by the radius of the wheel, or the radius of the circle. What this is going to translate into is linear velocity. Here's why. I'm going to prove it to you. Ready? I'm going to do a little proof. Because if you think about this, what is angular velocity? How did you calculate angular velocity? What's the formula for angular velocity? Theta, angular displacement, how far the angle travels, how many rotations, how many radians, whatever, divided by time, times r. Still with me? Well, watch this. This is craziness. What is theta times r really? Just look up. Arc length. Linear velocity is really the arc length divided by time. It's how fast you travel that linear distance that you've actually measured out. Yeah, huh? It's the same thing as linear displacement, not angular displacement. And I'll show you the difference here in just a second when I bring two of you up here. So think of it, angular velocity is how fast it's turning, how fast it's spinning. But linear velocity is how fast that spinning travels you along the road. Think of it as a car driving down the road. Your wheels spin a certain speed, right? The faster they spin, the faster you're going to what? Move along the road. So when you look back at the tire, imagine driving in the snow. The wheels turn a certain speed. There's your angular velocity. But then you know when you see the tire track laid on the ground, when you go through the snow, think of that as the arc length being laid out on the floor, laid out on the ground. That arc length is just being laid out. And really what you're doing is measuring the distance that you move along the ground. Okay? It's how fast you're actually traveling that distance around that circumference of that circle. It's not how fast it's spinning. It's how fast you actually have to run around the circle. And if you were to actually measure that out linearly as a straight line, did you see the difference? I can show you the difference right here. An example of this would be, if I was to take this Gatorade bottle, Sam, get up. It's going to be fun. Okay, Layton, come here.
You know you're recording.
Yeah. Sorry, Jack, you won't get to see this. But you can still live the experience. All right, so Sam's going to start walking around this Gatorade bottle. Now, he's not very far away from the Gatorade bottle, correct? Everybody see that? Not very far. Now, if I was to start to time him, stop a second. We'll start right there. Now, I want you to travel one rotation for me, and I'm going to see how long it takes you. We're going to see just walking one rotation. Let's see what your angular velocity is. Let's see how fast you go around the circle, or how fast you turn. Ready, set, go. Stop. He traveled 2 seconds, one rotation. So it's one rotation per 2 seconds, or 2 pi radians per 2 seconds, or 360 degrees. So we can figure out his angular velocity real quick. You say, okay, Sam's angular velocity was, he traveled one rotation, one rev, in 2 seconds. That's his angular velocity. But we never want it in revs. What do we want it in? Radians. So it'd be simple to convert to radians, because we know radians, you want to cancel revs out, right? One rev is worth how many radians? 2 pi, rad. Oops, I didn't spell rad right. It's spelled road.
Do you want us to label rad even though it's in...
Yeah, I do want you to label rad now. Tonight, I do. So then it would be 2 pi divided by 2, which ends up being what? Pi radians per what? Second. So that would be Sam's angular velocity. He travels 3.14 radians per second. Okay? goes about half a circle per second. He makes the whole circle in 2 seconds. So travel about that same speed. Now, you're going to be at a greater radius. So stand right by Sam, but you're going to be at a greater radius. I want you to be about that far away from the center. Keep up with him. Ready, set, go. Keep up. You got to keep up. Don't travel too fast, Sam. He's got to keep up. Keep up, Sam. Wait, I want you to be right by him, side by side. Go a little faster, Sam. We're going to make it more harder. I want you to look at this. What is the angular... All right, Sam. Keep going, keep going. What's the angular velocity? What are their angular velocities? They're exactly the same. Are they going around the circle the same amount of time?
Yeah.
They go one rotation at the exact same amount of time. One rotation every 2 seconds. Sam is going one rotation every 2 seconds. Leighton is going every rotation. But who is traveling a greater arc length? And that's based on what? The radius is greater, so what's changed? The linear velocity. His arc length, he's got to travel a bigger circle. And since he has to travel a bigger circle, his arc length is longer, which means he has to run faster. He has to march out that linear distance faster to be able to keep the same angular velocity. Their angular velocities are exactly the same. Their linear velocities are different. It's why when you run on a track and you go around the circle that they stagger the start. Lane 1 gets to start way back. Lane 2 starts up a little further. Why?
Because the distance.
Because the distance would not be the same. If they all started in the exact same spot, the people on the outer edge are going to run a lot further than the people on the inner edge. People on the inner edge wouldn't have to run as fast. Have a major advantage. So that's why they staggered start. You guys can sit down. So do you see the difference between linear and angular velocity now? Think of it. When you drive your car every day to school, you see 2 velocities at work. You ever looked at your odometer? There's 2 readings on it. What are they? Your RPMs and your miles per hour. What's your miles per hour measuring? That's linear velocity, how fast you move along the ground. What's the RPMs measuring? Angular velocity. Angular velocity of what? Let's see if you guys know.
Stick in the middle.
Yeah, stick in the middle. That's good. That's actually right. It's your piston. Your piston actually looks like this. And I don't know much about cars, but my brother explained it to me a lot. Kind of looks like this. There's a hinge point right here. This is a terrible drawing. And that piston kind of fires up and down. It goes like this, and it takes that hinge, and this thing goes in a circle. It bends there, and it travels a circle. The pistons, when they fire, go up and down. There's a circular motion that takes place. That RPMs is measuring how fast that piston's turning. And that piston turning, okay, is going to translate into the linear velocity based on the radius of the piston. That's why the bigger the motor, what? If you can get a faster piston and a bigger motor, what can you increase? So what they try and change 2 things in motors. How fast that piston's turning and how big the motor is. You got a small motor, can you have a real long radius? No, but maybe your pistons can fire fast. But there comes a point where you can only make the pistons go so fast, and so then what do? They lengthen the shaft, okay? They change the radius. So if they can change the radius and keep the same piston speed, then you're going to go even faster because you got greater distance. And if you're going that faster, you looked at Leighton, he was having to go, and I don't know a lot about cars. I don't know if that's how it goes, but you get the drift. Yes?
But shouldn't your car get faster than if you get bigger wheels? Like
Not necessarily. It's not totally related to that because your engine is what produces the speed, not the wheels. The wheels, the motion is transferred to the wheels. Now, if you look at the wheel, the faster your wheels spin, the faster you're going to go. But just because you change the wheel size doesn't necessarily mean you're going to change the speed because it's based on the circular motion of the piston, not the wheels. That's just transferred there. It's kind of a byproduct or an output of
That's
what's
just
happening
because
in the
when you
pistons.
look at a wheel, the further it goes out, like the bigger the radius is, the faster the wheel.
Slower it goes.
Slower. If the
So
wheels
you're
are
saying
smaller,
RPM,
the wheels
They'll go a little faster.
Yeah.
More rotations.
More rotations.
Because if you
Yeah,
go
more
the same
rotations.
speed,
Yeah,
if you got the same rotations and the wheel size were different.
The bigger wheel's not going to have to travel as fast as the smaller wheel.
That's what I thought. Like,
Yeah.
you have the same rotations with a bigger wheel.
So, but if you follow, are they still going the same linear speed?
Yes.
Yes.
Yeah, and it's kind of the thing that if you imagine a carousel, You know what a carousel is, right? Merry-go-round?
What do you call it, carousel?
Okay.
Carousel.
You ever rode on a merry-go-round at the park? The things that spin?
Those are dangerous.
You sit on the outside, right? If you want to feel like you're going faster. Now, the people on the inside look like they're going faster, but who's actually going faster? The people on the outside are actually traveling a much greater linear velocity, even though they're both spinning at the same rate. So if I decided to get on the carousel, okay, and there's 3 rows of animals, here's the center, and we got a row of animals here, a row of animals here, a row of animals here, and Austin jumps on the ostrich on the inside, okay, and Chris, total llama, alright, and Mo for show gets on the, me. I get on the stallion. All right, these things are bolted into the ground. They are spinning the circle at the exact same race. We're never going to win. Who's traveling fastest, though? I'm traveling the fastest linear velocity, but we're all spinning at the same rate. Okay, we're all spinning. We're all going around the circle. We're all going to make one rotation at the exact same rate. Okay, we're going to do one rotation in 5 seconds or 10 seconds or however fast this puppy goes, but the stallion's traveling much faster than the ostrich. It's having to cover a greater arc length. That makes sense. It's a little weird idea, but hopefully you get it. It's a little abstract, but you can think about it. It makes sense. The more problems that you do, the better. In abstract concepts.
Stop.
Now, go back over here just a second. I've got a bunch of conversions you need. There you go, write them down. All right, here's the conversions you're going to need.
Oh my goodness.
I've got circumference of planet Earth. Nobody found it. Actually, second hour, they did find it.
Oh,
The circumference of planet Earth happens to be 24,800 miles. How many think that's as big? Is it as big as you expected?
yeah, because there's 24 time zones. That's how I thought about it.
Wow, that's pretty impressive. Somebody said this morning 3,000 miles, and I was like, wow, we can go to California and back. All right, 24,800 miles. Actually, we can't even go to California and back. It's probably like 2,000 some miles to California. So 24,800 miles is the circumference of Earth. Now here's the circumference formula, 2 pi r. Everybody agree with that? Now watch how I solve this. Everybody look. Pay attention, you can write some more. If circumference of planet Earth is 24,800 miles, we can find the radius by setting it equal to the radius equation, 2 pi r. Divide by 2 pi, which if you do on your calculator, I want you to do it on your calculator right now. I need you to see you have to have parentheses around the 2 in the pi. If you don't, I want you to do it both ways, without the parentheses and with, and see what happens.
Why are you giving us the circumference here?
Because you're going to need it.
For what?
We're going to need the radius of your not circumference. You're going to need it.
So wait, if you're substituting.
All right, if you divide it by 2 pi, not only just divided by 2 pi on the calculator, she took 24,800 divided by 2 pi. She got 38,000 for the radius of the Earth. Does that even make sense? How can the radius of the Earth be bigger than the circumference? It can't. So what did she do wrong on her calculator?
Divided by 2.
Your calculator, when you divide by 2 pi like this without parentheses, it only divides by the 2 and it multiplies by the pi. Because it treats pi as something separate. So you have to put parentheses around the 2 pi. So don't clear that. Type in 24,000 divided by 2 pi.
I know that, but you just told us to do it that way.
Yeah, I know. I know she knew that. I just make you feel bad. Don't worry. For my
I think you're dizzy. He's went further distance than you did.
yeah, no kidding. Suck it up, Sam. Now you get, write this down, 39,047 miles.
Makes no sense.
Shh. 37. He's busier. 39,047 miles. You ready? Shh. I want you to round it. Let's go with 3950. So in your homework, when they ask you to do something with the radius of the Earth, let's use 3950 for the radius of the Earth. We'll just round it. That'll be easier to remember than 3947. That is the radius of planet Earth to the core. Somebody like, is it that exact? How do they measure it? There's mountains. How do they go through the mountains? I don't know. I don't care. It's close enough. Okay? Here's some other conversions you need. You need to know 2.54 centimeters is 1 inch. I didn't write this one down. How many inches in a foot? Yeah, 12 inches in a foot. Okay, you can handle that one on your own, right?
What does it say? L-I-N?
1 inch.
1 inch, sorry.
1 inch. That's it, L-I-N.
Little inch one. Inch. All right, pi radians is 180. Did everybody got that? Pi rad is 180 degrees. Got that one? What about this one? One rotation or revolution, and not the one Mr. Moser talks about. A revolution or rotation is one complete trip around the circle. So one rotation or revolution is 360 degrees or 2 pi radians. So whenever you see one rev or one rotation, you're like, okay, that's 360 degrees. That's 2 pi radians. All right, now, I put this here. This is the metric system. How many of you know the metric system really well? You should. He definitely knows it well.
Dude.
It's sad that you guys don't know
That's
this.
what he
That's what he.
That's all they is.
Joking.
He's joking. All right, shh, quiet. Quiet, girls. Metric. Oh, sorry. Metric. Here's how I remember this. You want to know the way I remember this? I don't know if they teach this over in Germany. King Harold's daughter makes delicious chocolate morsels.
Why
Muffins.
morsels?
Muffins. King Harold's daughter makes delicious chocolate muffins. Kilo, hecta, deca, meters, deci, centi, milla. Now let me just give you an example. Let's do 1 meter. Follow me here. 1 meter. I'll show you how to convert back and forth between this. 1 meter is how many decimeters? 10 decimeters. How many centimeters would it be? 100. Centipede, 100 legs. How many millimeters is it? 1,000. Millimeter, 1,000. When you get married one day, how many shoes your wife will have? Okay? Now, if you go backwards, even though I've got 10 to the 0 power here represents 1, I want you to see how many zeros you add this direction, how many zeros you take away this direction. 10 to the 0, 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, 10 to the first 10 squared, 10 to the third. This is how many more zeros there would be. But since we're starting with 1 meter, it's all based on where you start from. So 1 meter is 10 decimeters, 100 centimeters, 1,000 millimeters. What does decameters be? 0.1. What about hecta? 0.01. What about kilo? 0.001. Now let's try it different. Let's do another one. Let's do a red. Let's do 1 kilometer. 1 kilometer. Now we add zeros. What is it going to be? 10. What about deca? 100. What about meters? 1,000. Then what do we got? 10,000. What about this one? 100,000. What about this one? 1 million. You see how it works? You see how the metric system works? It's real simple. It's just multiplying or dividing by 10.
What's the green?
Well, that was I did 1 meter here, and I went from 1 meter. I converted 1 meter back and forth.
What are these?
I did 1 kilometer.
What's that? I, E, E, C. Between the King, Harold, whatever.
Underneath
Go-
it.
go
Kilo,
hecta,
hecta, deca,
Ah,
meters,
oh yeah, I
deci,
got it.
centi, milli. All right, real quick. 1 mile, 5,280 feet. Everybody got that one? 1 yard, 3 feet. Everybody got that one?
I hope.
Okay? Those are the common measurements you'll need to be converting between. Okay? Ready to do a couple examples? You gotta go quick. All right, I want you to find the angular velocity. Okay, here we go. Angular velocity. And I'm gonna change it a little bit. I'm gonna make this, and we did 1 second, but let's do 3 seconds. Now, some of you are like, well, you're not really asking a lot. You're just asking us to divide 2 numbers. I know, but the main thing you gotta understand with angular linear velocity, the units have to be correct. Specifically, the angle. What do we need the angle always to be measured in? So they're gonna give you revolutions sometimes they're gonna give you degrees, and you need to make sure it's in the correct units. So if they give you revolutions or degrees, you're gonna have to convert it to radians. But yes, angular velocity. How do I calculate angular velocity? How do I calculate?
Over time.
Angular displacement, how many rotations, how many clicks you get in the circle, how many times it turns, divided by the amount of time it takes to turn those turns. Okay? So, how far did it say I traveled? 4/5 of a rotation. It didn't even go a whole rotation. It only went 4/5 of a rotation. So I hit the gun, and in 3 seconds, you only made it 4/5 of a rotation. So maybe it was like the whole circle around here. Maybe it was, how far can you circle the room? And you only made it 4/5 the way around in 3 seconds. Okay? So omega would be what? 4/5. But what is that measured in right now? It's in revs or rotations. Revs and rotations, same things. Divided by what? Time. Now time doesn't matter unless they say it matters. So unless they tell you a specific time, if they say minutes or hours, you got to put it in whatever they tell you to put it in. But is there any preference here?
No.
No, so let's just leave it in seconds. Divided by 3 seconds. Now, do you like revs?
No.
No.
I don't. Let's go ahead and we'll deal with the revs in just a second. So let's simplify this a little bit. How can I do 4/5 revs divided by 3?
Put 'em in.
How can I deal with the 4/5 divided by 3?
Converted.
I can go back to 7th grade. 4/5 divided by 3. How do we do this? It always struggle, calc, every year. How do we do 4/5?
Divided by 3.
You're going to go 4/5. When you divide a fraction by another number, you got to multiply by the reciprocal. That's why I did this, because I want to make sure you got it. So this is actually going to be 4/15 revs per second. Now let's do the conversion. Let's convert this baby. How can we convert revs into radians?
Do you always want it into 1 second instead of going over 3 seconds? Like,
Well, it's going to be 4/15 right
yeah,
now.
I know, but like, I didn't.
The one rev on the bottom.
Like I just converted it to radians, right?
Oh, you could have done that too. Yep, that would have worked. We should still get the same answer. Okay, convert to revs. How do we do it?
Rev.
Revs, if we want revs to cancel, where's it got to go?
On the
Bottom.
Bottom. What do we want on top? What's the conversion between revs and radians? 2 pi radians per what? 1 revolution. Revs cancel. Let's multiply this puppy out. What are we going to get? 8 pi over 15 radians per second. There is your angular velocity.
So I got 8. Okay, I just think I got the same thing. I just
You
didn't
could convert it to radians first, then do all the math.
because I have 8 over 5 radians divided by.
You got to simplify
seconds.
that. Do
Yeah,
not
I know.
anyway.
I was wondering if you
Yeah,
just
you need to simplify. So 8 pi over 15 radians per second. Does that make sense? Angular velocity is simple. It's going to get hard when we do linear here. Okay? All right, let's do this one. So, this problem, find omega in radians per second of a wheel traveling 25 revolutions per minute. Find omega, find the angular velocity in radians per second of a wheel traveling 25 revolutions per minute. Now, what is 25 revolutions per minute? What is that? What does that happen to be?
Linear.
Revs.
No, it's not linear.
Not linear, but it's the.
Omega.
It is omega. 25 revolutions per minute is omega. That is the angular velocity. But what is it not? What are they asking?
In seconds.
We want it, and we don't want it in minutes. What else? We want it in radians. This is rotations. They would have specified in the directions. It'll say rev per minute. They'll have a parentheses to make sure. So we're going to have to change. So the angular velocity, that is the angular velocity. It's 25 revs per minute. But what do we want it in?
1 in radians per
We want it rads per second. So all this is a conversion problem.
Well, we want rads per second.
We want it rads per second. So let's do this. Let's do it all at once.
Shouldn't we do it to seconds before we do?
It doesn't matter. You can do it all at once. All right, let's go. Let's do the rev. Let's deal with the rev first. How would you deal with the rev?
1 revolution.
1 rev on bottom. To get the revs to cancel, the revs got to go on bottom. What goes on top? 2 pi rad. Keep going. Revs will cancel. We got our radians, but now it's in radians per minute.
Seconds. 60 seconds.
All right? Where do the seconds got to go?
Top.
Bottom.
They got to go on bottom. Because we want to cancel minutes. Minutes is on bottom. Where do minutes got to go?
Oh, I see.
Minutes got to go on top to cancel the minutes. Seconds go on bottom. What's the conversion? 1 to 60. Do the minutes cancel? Good. Can we do the math here? Real fast? What's 25 times 2?
50.
50 divided by 60. Reduces. The zeros cancel. What do you get? 5 pi over 6 radians per second. There it is. That is the angular velocity in radians per second. So you've done a couple of converting problems. Let's do one more. You got a linear velocity. Okay? Hold on, we're almost done. Oh yeah, this one's massive. All right, here's what I want you to do on this one. We'll read it to you, and we'll do it, and this will be the last problem. Okay? All right. The wheel of a truck goes round and round. The wheel of a truck is turning at 6 RPS, revs per second. What is that?
Omega.
That's omega. That's your angular velocity. The diameter of the wheel is 4 feet. Question A, find omega in radians per second. Part B, find V. What's V stand for? Linear velocity in feet per second. So go ahead and try it.
Omega is already in.
Yep, then we have to.
Oh, it's
convert it.
revolutions. Never mind.
Okay? So go ahead, give it a whirl. Go ahead and try part A real quick. Find omega in radians per second. This will be the last problem. Everybody do it with us. Don't pack up yet. Tomorrow we'll look at pulsars. It's going to be intense. I'm going to turn the volume up loud. It's going to be annoying. It sounds like little flywheels.
Velocity.
Omega. All right, part A. I want to find omega. We already know what omega is. What is omega? 6 revs per second. So all we're doing to this one is conversions. So what do we want to do to convert 6 revs per second into what they want, radians per second?
2
You
pi
could
rad
just-
over 1 rev.
All I got to do on this one is just go 2 pi rad. People are going to ask me, do I need to show that work?
No.
I recommend it. I'm not going to make a big deal about it, but just be able to explain how you did it. Now, these problems, some of them are going to be conversion nightmares because you're going to be converting like 6 or 7 things. So sometimes you're going to want to write out the work. So make sure I'm going to keep writing it out so you learn to do it. The revs cancel. What do we got?
12 pi.
12 pi rad per second. Have we done part A? Have we answered part A?
Yes.
We have found the angular velocity in radians per second. Part B, how do you calculate linear velocity?
Omega times radius.
Omega times radius. What is omega?
6 pi is 12 pi.
12 pi. Can't use, this is the thing, linear velocity only works when angular velocity is in radians. It doesn't work in degrees. It doesn't work in rotations. That's why you got to do conversions. So it's radians per what? Second. What's the radius?
2.
Very good. How'd you know the radius is 2? Because I gave diameter. It's half the diameter. So that's going to be 2 feet. Now let me show you what happens with the units here. Because we just proved a few minutes ago that if you look at linear velocity, omega times r, this was really theta divided by t times r, which was really arc length divided by time. We really want, since it's really arc length, and arc length is really just a length, radians mean nothing now.
So can we just go?
That's the only way this works, because degrees and rotation won't do that. It has some more meaning that's not really related to a length. Radians, the reason we use radians is because it's related to a radius length is why we can use it. So you drop the rad, and it ends up being 24 pi what? Feet per second. There it is. There's your linear velocity. Any questions? And you can actually multiply that out and see what it is. It's going to be about 72 feet per second, approximately. Did everybody know what their homework is?
Yep.
All righty. Good job today.
Go get your food now.
I'm going.
You want